Hi, this video is about the main reason we think light is a particle, and it all comes back to this one experiment known as the photoelectric effect. Now let me explain how this experiment is set up. We start with a glass tube that has all of the air sucked out of it, a vacuum tube, and on each end of the tube we have some pieces of metal. On one end we just have a standard piece of metal here, and the other end we pick a piece of metal that is sensitive to light. It's known to produce electrons when light shines on it. And we set these two pieces of metal up in a little electric circuit of sorts, except it's not a connected circuit. Instead, it's just got this end over here attached to the positive terminal of a battery, and then this end over here attached to the negative end. And we have an ammeter set up over here. This measures how much electric current passes through. Now, right now, you'll notice it's not a circuit because there's no connection in this vacuum tube. There's no electricity able to pass through this empty chamber. But when you shine a lamp onto this light-sensitive metal, it can generate electrons, and electrons will be taken off of the metal and allowed to move freely. And since electrons are negatively charged, they're going to be attracted to this positive metal. So if we turn the light on, we should see electricity flowing through this circuit because electrons are being freed from over here, and then they travel to this positively charged metal and through the wires, through the ammeter into the battery, and the circle continues here. So this is the photoelectric effect experiment setup. And if light is a wave, as most people at the time thought when this experiment was first done, then there are certain things that should happen here. So let's talk about those expectations. If light is only a wave, then there are three main things that should happen when you shine this light onto a piece of photosensitive metal. The first expectation is that there's going to be some lag time between when the electrons actually are freed and when you shine the light on it. It should take time for electrons to build up enough energy to finally break free and jump off of their atoms and start moving through the circuit. So you shine the light and you have to wait a few seconds or maybe a few minutes for there to actually be any electricity going through the circuit. That's expectation number one. Expectation number two is that freedom is colorblind. The electrons can break free no matter what color of light you shine on, because all light has energy in it. So if you shine a red light or a blue light, you should get electricity passing through this circuit. And then the third thing is the brighter light should result in faster electrons. The reason for this, the thinking goes, for a light wave, if you have a brighter light wave, that means the wave is kind of waving up and down at greater amplitudes, which has a bigger punch to it. So this gives electrons a harder kind of final push to make them go faster when they're freed. And so a brighter light should make the electrons move faster across the vacuum tube. I imagine a good way to imagine this is it's kind of like riding a swing and trying to jump outside of the mulch around the swing set. I don't know if you ever try to do this. I do this all the time, right? So if you're riding on a swing surrounded by mulch here and you're trying to jump outside of that, you're going to have to build up enough speed. It's going to take you some time to build up enough energy as you're swinging back and forth to finally have enough height to jump clear of the mulch. Second, it doesn't really matter what color shirt you're wearing. That has no effect on the ability of your swinging to jump outside of the mulch. And then the third thing is, the third kind of comparison I made here is, imagine you had like somebody pushing you to kind of give you an extra push. Like if you have a brighter light, it's kind of like having a stronger person pushing you. So if you have a really big, strong, person trying to give you a push, they can kind of help you clear the mulch a little bit easier and a little bit further. So these are the expectations that we would expect if light was acting as a wave. Then these things should happen when we do the photoelectric effect experiment. Now you might be guessing at this point, this is not exactly what happens. The reality is a different story. The reality of this experiment was quite a different story. instead of there being lag time where the electrons had to build up enough energy to jump off, the electrons instantly jumped off when the light shined on the metal. There was an instant energy delivery. As soon as that light was turned on, electrons were able to jump off. That was unexpected. And a second thing that happened, only certain colors could actually cause the electrons to jump off. There seemed to be a certain cutoff for each different type of metal that you used. Colors that were closer to the red end of the rainbow could not free the electrons no matter how bright the light was. And the third kind of unexpected reality of this photoelectric experiment was that brighter light only made more electrons, not faster electrons like we would expect. With high amplitude light, you expect fast electrons. However, the brighter light only made more electrons, but it didn't actually make those electrons move any faster than before. So what are we to make of all this? If light is a wave, we should expect these things, except we don't see those things in reality. We see these unexpected phenomenon here. And so the solution was proposed by a man named Albert Einstein. I don't know if you've heard of him. But Einstein's suggestion was that a beam of light can only carry energy in discrete packets or particles, rather than a single kind of uninterrupted stream of energy, like a river of energy. Light was made up of these individual pieces. And one individual packet or particle of light is called a photon. And this idea of photons goes back even before Albert Einstein, even all the way to Isaac Newton, who thought light could be made up of these little pieces called photons. And one of the things that one of the characteristics of photons is that they act alone. Each absorbed photon will instantly give away all of its energy to only one electron. And then that photon ceases to exist after that. So they're just these energy delivery devices that as soon as they deliver that energy, they're gone. And the only way to pack more energy into a single photon is to raise its frequency. Because it's an individual piece, the only thing you can do to make it have more energy is to raise its frequency. A brighter light means more photons and more overall energy, but the energy per photon remains the same. So these explanations help to make sense out of the reality that we saw before. So while light clearly shows signs of being a wave in other kinds of experiments, if we view light as a particle at some points, then we can start to make sense of this reality. How can light deliver so much energy so quickly, and why does it depend on the color of the light? Well, red photons, according to Einstein, always have lower energy because they're low frequency colors. And even if there are a lot of red photons, in other words, there's a high brightness of red light, their individual energy deliveries are never strong enough to free an electron. So this explains why red lights and other low energy lights could never actually make the photoelectric effect happen. On the other hand, blue photons always have high energy, and even if there are only a few of them and the light is very low brightness, all it takes is just one blue photon getting absorbed to free an electron. So finally, we're able to make sense of this one particular experiment, and this one photoelectric effect experiment is the main reason that we think that light is a particle, at least at times. Light is both a wave and a particle, and it behaves differently in different situations. So that's all I've got for you in this video. Remember, the opposite of love is not hate, but apathy.